In this video, we're going to start talking about the first of the two questions that calculus is really about, and that is finding the slope at any point on a curve. Now, what I've given you here is a graph that has distance and time. So you'll see that we've got time on this axis, distance here. So if I said to you, at what distance away is this object 20 seconds in, you'd say, well, 20 seconds in, the object has moved 40 meters, or is 40 meters away. If I said, well, okay, what about at 90? You'd say, well, at 90, it looks like just under 70, maybe like 68 or something like that. At 130, well, it's 150 meters. So this is a distance graph. So we've got meters here, and we've got time in seconds here. So here it says find the velocity. Well, I'm going to use some units here. A lot of times thinking about units is really the easiest way and best way to think about how we get one answer from the information we've been given. So velocity in this case would probably be in meters per second. And again, we've got meters on the y-axis. We've got seconds on the x-axis. So if you're thinking about, okay, it's how much of a change in the y-axis there was in relation to the x-axis, meters per second is really change in y over change in x. Velocity here we're going to get by finding the slope. Okay? And again, that's all from units. Meters per second, on our graph, I'm going to write it up here, meters per second really is the change in y and the change divided by the change in x. Okay? So the velocity from 0 to 20, well, we're really just finding the slope. Okay? So, we could do this with points. We could just say, well, it went up 40 units and it covered 20. However you wanted to do it. But it does have a, run of 20 and a rise of 40. So 40 divided by 20 would be 2 meters per second. So that's the velocity. Next question, we're looking for the velocity from 20 to 60. Well, here's 20, here's 60. The slope is 0. And from a standpoint of just thinking about the graph, if I tell you 20 seconds in, this object is 40 meters away, and it doesn't move, and it doesn't move, and it doesn't move, and it doesn't move, and at 60 seconds, it's still 40 meters away. Well, what's its velocity? Well, 0. It hasn't moved. So hopefully that makes sense, why that works out. And finally, find the average velocity from 60 to 120. So here's why I say average. There's 120 right there. The velocity here, the slope, was always 2. Here the slope was always 0. If you wanted to go further, the slope will always be 0 up here between points D and E, and it will always be constant here. But here, the slope is steepest in here. Okay, it gets steeper as we go up. So it starts off not very steep, and then it gets steeper as we go on. Okay, so we can't say what the actual slope is at every point between 60 and 20. Instead, we're going to say what the average is. So what we're really calculating here, I'm going to just kind of do a dotted line, is the slope between those 2 points. So this point is 60, 40, and this point up here is 120 and 150. So the slope would be the change in y over the change in x. So we've got 110 divided by 60, or 11 over 6 meters per second. And that's the average velocity. That's the slope. So let me change the question. What if I didn't say find the average? I actually said find the slope, or find the velocity at 90. Again, we're talking slope. And think about units, if that's confusing. If you say, well, I don't understand why the slope is going to give us velocity. Think units. Meters per second, change in y over change in x. So here we are at 90. I'm going to put that point in there. I want to try and estimate the slope at that point. And you'll see again, the slope down here when it first starts moving, this object again is not, the velocity is not very big. The slope is small. Up here it's much bigger. So the slope changes throughout the graph. So a good way to think about this is to pick a point on either side. Maybe let's just go, like 80 and 100. Something like that. Pick the points on either side. And we might have to do a little estimating and say, well, this looks like the point 80, comma, 53, let's say. And this looks like the point 190. So our velocity would be, again, the change in y over the change in x. So we've got 37 over 20 meters per second. Now that's an estimate. If I wanted to get a better estimate, instead of picking 80, I could have picked 85 and 95. If I wanted an even better estimate, I could have picked 89 and 91. I chose an easy one here by just using the grid on the graph, but again, this is completely, I'm going to circle the word estimate. This is an estimate. That is not the actual slope, but it's a nice guess about what the slope is. And this gets us to that big question in calculus. How do we find the actual slope at one singular point? Okay, let's move on. In this example, I'm not talking about speed anymore. I'm talking about a pot that is put onto a stove. Okay, so we've got the degrees and the number of seconds. So find the average rate of change from 0 to 100. So let's do that from 0 to 100. And again, you'll notice it's not quite linear between those two spots, and in fact it looks like it changes slope. Here it's steeper, it looks like it levels out a little bit up here, and then it totally levels out right there. So let's think about this in terms of just points again, like we did on the previous example. We're going to have a point 0, 10, and up here we're going to have the point 100, comma 100. So if I'm thinking of slope, the average rate of change means slope, I've got 100 minus 10 over 100 minus 0. So I've got 90 over 100, or 9/10. And let's use some units here. We've got the change in y, so degrees, over change in x, so per second. So it's going up 9/10 of a degree per second. Now, finding the instantaneous rate of change at 20. Well, this is going to be a little harder, because now we're looking for the slope right there. So notice the difference here between an average, which just says between here and here, between these 2 points, how's it going up on average? This is saying at that spot, how fast is the temperature increasing? Well, I think the easiest way, again, is to just pick a point on either side. We already have this point at 0, 10. This other point looks like 40, 60. So let's find the slope. 60 minus 10 over 40 minus 0. So 50 over 40, or 5/4 degrees per second. Now, I just want to point this out. We said it was a little bit steeper. The slope here is a little steeper than up here, right? And then, of course, here it was level. Well, our average rate of change from 0 to 100 was less than a degree per second. But at 20 seconds in, it was greater than 1 degree per second. So that verifies the slope is greater here at 20 than it is on average for the whole thing. Okay, so it's the difference between this idea of an average and the idea of an instantaneous rate of change. Now, how could we make the estimates better? Well, instead of picking those 2 points, instead of picking, 0 and 20, what if instead we picked 10 and 30? Or 19 and 21. So a smaller interval will get us better estimates. Again, I'm just kind of using the graph to give me my best possible, give me an idea, a rough estimate, but the closer I got, the better it would be. Now in this next example, I'm not giving you a graph. Okay, and you can read here, this is a pebble is stuck in the tread of a car. As the wheel turns, the distance in inches between the pebble and the road at various times in seconds is given on the table below. And I say find the average rate of change. Well, average rate of change, remember, is just a slope. So it tells us time 1.2 and 1.6. So I know that's the estimate, or that's the x part of my estimate. So 1.2 and 1.6 are right there. So let's do 0.22 minus 0.63. Okay. And we could calculate that. Now, in the interest of time, I'm going to just kind of move through this a little bit. The unit would be inches per second, okay, because it's a rate of change. Now, moving on here to the next question says, how fast is it changing at 1.4? So now I'm saying, well, okay, I don't want to know on average. I want to know right here, how fast is it changing? Well, remember on the graph, we picked spots on either side and kind of used that to connect and estimate the slope. I'm going to do the same thing here. I'm going to pick the 2 spots on either side, and I'm going to do change in y over change in x. And again, it will be inches per second. So if you're looking at this and saying, well, isn't that an average rate of change? It is. I'm estimating the instantaneous by simply using a small interval to get the average. Okay. So how fast is it changing at 1.8? Well, again, we do the same thing. We pick a point on either side, and we do the slope, inches per second. Now, how would we make these estimates better? We'd need a smaller interval. Again, all we're doing right now is finding the average rate of change. The smaller the interval, the closer it gets to being an instantaneous, but it's not instantaneous. It is an average. Okay, let's do one more problem. Okay, in this example, we have a door with a spring hinge swings open then closes. At time t seconds, it forms an angle of d degrees with the wall. Let d of t be 200t multiplied by 2 to the negative t. First question is find the angle at 1 second. Well, you'll notice this is not asking for a rate of change. This is just saying find the angle. Well, we have an equation that does that, so we would just plug 1 in, d of 1. Well, 200 multiplied by 1 multiplied by 2 to the negative first is 100 degrees. Okay. Now, estimate the instantaneous rate of change. Now, again, remember this means slope. We're going to find the slope of this exponential equation. So the nice thing about this, in the previous examples, we had a graph and we picked points on either side that were kind of easy to identify, or we had a table where we were provided with points on either side that we could identify. But now with the equation, we could actually pick any points we want. So here's what I'm going to start with. I'm going to write this interval notation. I'm going to go from 0.9 to 1.1. Okay, so again, we're trying to estimate the instantaneous rate of change at 1. So think about what, if this looked like this, and we want to know the slope here, we're going to pick a point on either side, find the slope between those points, and say, oh, that's a pretty good estimate of the slope at that red dot. So finding the slope like that, 1/10 on either side, I would plug that into my calculator, 1.1 and 0.9 to get the y values, and I do that and I get 102.634, so 102.634 when I put 1.1 in, and when I put 0.9 in, I get 96.460. Or excuse me, 96. So I'll actually calculate that slope, and I get a slope of 30.87. Okay, so that's not a bad estimate of the slope. It's only a tenth away. But with the equation, why couldn't I get even closer? So let me do 0.99 and 1.01. Okay, and I'll put this work right down here. And I plug it in. And I calculate it, and I get 30.65. So this is probably a better estimate than my original because I picked points that were closer. Okay, let me go another. Now, because we're getting so close, I actually did this on my calculator and didn't necessarily use the rounding that I cut to 3 decimals. I went further out because, as I said, I'm only 1,000th away. And what I see is when I do this, I get 30.68. Now, the actual slope there, if you actually could find it, is 30.685. So we started off at 30.87, so not a bad estimate, only going a tenth on either side. Then we went 100th, we got really close, and then we went 1,000th, and we're almost there. So this is the big idea behind this. All of these things is that as we pick points that are closer and closer and closer to the value we're interested in this case it was time 1 second, as we pick points closer and closer, we get closer and closer to the actual answer. So we say that this is what's called a limit, that as we make our intervals smaller, okay, so as these intervals get smaller and smaller, the limit is the actual answer. And you'll see that by going from a tenth to 100th to 1,000th, how close we have gotten to the actual slope.